What's up, guys? Welcome to Calculus Club. In this video, we will be talking about evaluating limits analytically. Okay, so in the previous video, I talked about finding limits when you are given the graph or using a table to find the limit. In this video, we're going to use tools in algebra in order to find the limit. All right, so let's get started. All right, so to get us started, I want to first give you a few simple limits, okay? So pause the video and think about what each of these limits will equal. All right, so I hope you paused the video and you tried that. Now, each of these, the good thing about this is all these limits are continuous, so it's pretty easy. All you really need to do is plug in, right? Remember, normally it's the limit as x approaches a of f of x. So this x squared, and this 3 are just f of x in each case, okay? So for the first one, the limit as x approaches 2 of x. I just plug in 2. And you can see here, here's the graph, right? The limit as x approaches 2, here's from the left, here's from the right. You're approaching to that value of 2, okay? The limit as x approaches 2 of x squared, again, all I need to do is plug in 2, and I get 4. Here's what the graph looks like as I approach 2 from the left, and as I approach from the right, I'm approaching the same y value, which is 4, okay? So this third one is a little bit more tricky. All right, some students have a little trouble with this one, but after I show you, I think you'll understand. So the limit as x approaches 2 of f of x equal 3. All right, so this is the function f of x equal 3, this red line. Well, as we approach 2 from the left, and as we approach 2 from the right, we're approaching the same y value, which is 3. So the limit as x approaches 3 is just going to be 3. All right, and that's always going to be true if you have the limit as x approaches a of any constant c, right? That will just be equal to the constant c. All right? Okay, so as I just said, if a function is continuous, then all you need to do is plug in the x value and you will get the limit. The limit will be equal to the y value, the f of x, the f of a, if the limit as x approaches a. All right, so I'll give you a couple examples. Go ahead and try both of these. All right, so I hope you tried both of these. All you need to do is plug in. So the limit as x approaches 3, x squared minus 5 is just 3 squared minus 5, which is just 9 minus 5, which is 4, okay? The limit as x approaches negative 1 of this one is just negative 1 cubed minus 2 times negative 1, which is just negative 1 plus 2, which is just 1 on that, okay? So if a function is continuous, it's super easy to solve. When the function is discontinuous, it becomes a bit more complicated, okay? So when is a function discontinuous? Well, generally assume a function is continuous, okay? Generally functions are continuous unless there's just a few specific cases where a function is discontinuous, okay? The first example is when you divide by 0, okay? So at x equal 3, you would get 0 in the denominator, okay? You cannot do this in mathematics. If there's a 0 in the denominator, we're not sure exactly what's going to happen. It could be a hole, like in this one. If I were to graph this function, okay, this is what the graph looks like, and you can see at x equal 3, there's a hole. This also could be a vertical asymptote. If you get a number over 0, that's going to be a vertical asymptote, and we'll talk more about that later. But just keep in mind that when we divide by 0, a function is discontinuous. You can have 0 in the numerator, that's no problem. 0 divided by 5 is just 0, okay? That's perfectly legal in mathematics, but you cannot divide by 0. So that is the most common case where you're going to have discontinuity, where the limit becomes a little bit tricky. But we do know the limit as x approaches 3 of this will just be 4, right? Because we're both approaching 4 from the left and right. We can see that graphically. Another example is when you have a piecewise, okay? So this piecewise, notice at 0, if it's less than 0 or equal to 0, you get 2. And then if it's greater than 0, at 0, it would be 1. So this piecewise, these two do not equal one another, right? So I approach from the left, I get 2. I approach from the right, I get 1. So the limit as x approaches 0 of this one does not exist. A piecewise is another place where you might have discontinuity, okay? So there aren't that many cases where you might have discontinuity. You could have divide by 0. You might have a piecewise, okay? A square root of a negative is discontinuity. Also the natural log, which we'll talk more about if you're, if it's been a while since you've studied that, but you cannot have the natural log of 0 or the natural log of a negative number. Those could also be discontinuities. And the square root of a negative, okay? Not sure if I just said that. But anyway, just a few cases where you have discontinuity. So generally a function is continuous unless you have one of those circumstances. And in a later video, I will talk more in depth about this, okay? So let's talk a little bit about an analytical understanding of a point of discontinuity, all right? So what I want you to do is I want you to take this function f of x, which equals x plus 1, and I want you to take this g of x plus 1 times x minus 3 divided by x minus 3, and I want you to evaluate the x values for the different numbers you see there, 0, 1, 2, 3, and 4, okay? So pause the video and fill out this table. I think it's really important you do this yourself. So please pause the video and try this on your own. All right, so I hope you've paused the video and you filled this out on your own, okay? So let's fill in the f of x's. Those are pretty easy, right? X plus 1, so that's 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 1 is 4, 4 plus 1 is 5. So I hope you got 1, 2, 3, 4, 5 on these f of x's, all right? The g of x, well, when we plug in 0, what's gonna happen? Well, we're gonna get, so g of 0 is going to be, and I'll just write these here. G of 0 would be 0 plus 1, 1, negative 3, which is a negative 3 over a negative 3, which is a 1. So you get the same value for g sub 0. G sub 1, if I plug it in, all right, so my g sub 1 is going to be 2 times a negative 2 over negative 2, which is negative 4 over negative 2, which is a positive 2. So I get the same value there as well, okay? So for lack of room, I'm just going to erase these real quick. Let's try the next one, g of 2. All right, so when I plug in g of 2, what happens here? I get 3 times negative 1 over negative 1. Negative 3 over negative 1 is 3. I get the same number. Now g of 3 is the funny one because when I plug in g of 3, I get 3 plus 1, which is 4, times 3 minus 3, which is 0, over 3 minus 3, which is 0. This would be 0 over 0, and the bigger thing is I have a 0 in the denominator, which means discontinuity. The function doesn't exist there. So for this one, the function does not exist. Okay. When I plug in 4, what do I get? Well, I get 5 times 1 over 1, which is just going to be 5. All right. So notice these two functions, right? Well, first of all, to go from f of x to g of x, all I've done is multiplied by x minus 3 over x minus 3. X minus 3 divided by x minus 3 is just 1. So really, all I've done is multiplied by 1. So this is not going to change any of the y values, right? But what does change is because you add in an x minus 3 to the bottom, you create a discontinuity at 3, okay? So if I were to graph these two functions, this is x plus 1, this is g of x. These two look exactly the same, except for at x equal 3, there is a discontinuity, okay? Now, why do I show you this? Well, the reason is that while the g of 3 does not exist, let's talk about the limit as x approaches 3 of g of x, well, this is just going to equal to 4. And this also equals the limit as x approaches 3 of f of x. Okay? So, in knowing this, if I were to ask you what's the limit as x approaches 3 of g of x, well, you could just eliminate, you could cross out x minus 3, and you could say the limit as x approaches 3 of g of x equals the limit as x approaches 3 of f of x, or x plus 1, okay? Those two will be equal to one another, all right? So, let me talk a little more about this, okay? So if I were to give you, so this is what we've already done. So what if I were to just give you something like this? What's the limit as x approaches 3 of x squared minus 2x minus 3 over x minus 3? Pause the video and think about this for a second. All right, so I hope you pause the video and I hope you notice that actually x squared minus 2x minus 3 is x plus 1 times x minus 3. Those two are exactly the same. Okay, so that means that what we can do is you can rewrite this as those are exactly the same, and because the x minus 3's cross out, you can say that the limit of all of this, the limit of either of these, will equal the limit as x approaches 3 of f of x, which is just 4. Okay? So if you can cross out a factor on the top and bottom, then you will be able to find the limit. Because when you can cross out a factor like that, all you have is a point of discontinuity. You just have a hole, okay? So that limit still exists and equals the new limit when you eliminate the x minus 3. All right, so now I have a problem that I want you to try to solve on your own, okay? Try to find the limit as x approaches 2 of this function. Notice at 2, there is a discontinuity because we divide by 0. All right, so I hope you paused the video and you tried this on your own. Okay, so how to do this one? Well, what we're going to do is we're going to factor the numerator. All right, so we're going to get the limit as x approaches 2 of x plus 3, x minus 2 over x minus 2. Okay, we can cross out the x minus 2 and we'll find that this equals the limit as x approaches 2 of x plus 3, which is just 5, okay? So I hope you didn't have any trouble with that one. Let me show you with Desmos, just to show you that these two functions are equivalent, okay? So x squared plus x minus 6 divided by x minus 2, right? You're going to get that. And then we showed that that equals 2, y equals x plus 3, right? And you can notice the red and the blue are exactly equivalent. The only thing is you would have, on the red at 2, you would have discontinuity. And it's not going to let me highlight 2, undefined. So you see you have that hole there, okay? All right, so moving along. So the next way that you can use algebra to find a limit is you can rationalize the numerator. All right. So let's say I give you this function, the limit as x approaches 0 of square root of x plus 1 minus 1 over x. Well, first thing we always try, plug in that 0. Let's see if the function is continuous. All right. We plug in the 0 and what happens? Well, we have a 0 in the denominator, okay? So function is discontinuous, all right? So we're gonna need to do some more work. There's nothing here that can be factored. So what we're going to do here is we're going to rationalize the numerator. Okay, so how do we rationalize the numerator? Well, what you're going to do is you're going to take, instead of square root of x plus 1 minus 1, you're going to multiply the top and the bottom by square root of x squared plus 1 divided by square root of x plus 1 plus 1, okay? And you can do this because, again, all you're doing is multiplying by 1, okay? So you're not changing any of the y values. All you're doing is, if there's a point of discontinuity, you're filling it in, okay? So let's do it. When we multiply these out, we're going to get the limit as x approaches 0 of, all right, so we're going to have to multiply square root of x plus 1 by both of these. All right, so you're going to get square root of x plus 1 times square root of x plus 1 is just x plus 1, right? Square root of 3 times square root of 3 is just square root of 9, which is just 3, okay? So you're going to get, in the top, you're going to get x plus 1. And then you're going to get plus the square root of x plus 1. All right, and now you need to multiply this negative 1 by both of these. So you're going to get minus the square root of x plus 1 minus 1 over the bottom is going to become x times square root of x plus 1 plus 1, okay? Now what happens is we have a lot of stuff that crosses out. Square root of x plus 1 minus square root of x plus 1 is going to go away. 1 minus 1 is going to go away. And you're going to be left with the limit as x approaches 0 of, you have only an x on the top, divided by the bottom is just x times square root of x plus 1 plus 1. Notice what else is going to happen? Well, these x's are going to go away. So I'm going to cross out these x's, and I'm going to be left with the limit as x approaches 0 of 1 over the square root of x plus 1 plus 1. Okay? Now I'm going to plug in the 0. And look, now we no longer have a discontinuity because when I plug in the 0, I'm going to get 1 over square root of 0 plus 1, which is square root of 1, plus 1, which is going to equal to 1 over 2 equals to a half. And we arrive at our conclusion that the limit of all of this equals to 1/2, okay? And then let's just check this. So I advise you to try this right now. Use Desmos, use a calculator. Go ahead and graph this and make sure you get the same answer, okay? If you want, you could also graph this one, and you'll see that those two are identical, okay? All right, so I hope you did that on your own to just give you some extra practice. A lot of times I'll tell you to do stuff on your own because this way it'll stick in your mind a little bit better and you'll remember it, okay? As opposed to if I just tell you how to do it and you just follow me and copy everything I do, you're not really gonna learn it in a thorough way as opposed to struggling and doing things on your own, okay? So just a little aside there, often during my videos, I will ask you to do something to struggle with it because that's the way that the neurons in our brain form stronger connections and we really understand what's going on, all right? So yeah, so if you graphed it, you should have got something that looks like this, and we can clearly see the limit as we approach 0 from the left and from the right equals to 1/2. Also, if you check it with the table, you'll see that both of these are getting closer to 0.5, 0.5. All right? So yeah, so that's all for the algebraic analysis of limits. So I hope this video was helpful. In the next video, I'll talk a little bit about the properties of limits. And after the next video, you'll be pretty well equipped to solve quite a few limit problems using algebra without the need of a calculator or Desmos. But I always advise you check those answers with calculator or with Desmos, okay? All right, thanks for watching, guys, and I hope you continue to tune in and this video was helpful for you in your calculus journey. All right, bye-bye.